Okay, so we're going to look at a supplemental thing. This may or may not be part of the AP exam, depending on which exam you're taking, and it doesn't show up every single time, but it is something that ties stuff to real life, so I want to talk about it very briefly. It's the sort of thing that is just a small addendum onto stuff we've already done. It's called internal resistance. Now, on the APC exams, they do like to ask questions about this. On the AP1, I can't remember if they'll ask or not. And AP2, I expect they'd probably have questions like it, but it's a relatively small addition. So let's talk about, and it helps tie things to real life. Let's talk about actual batteries. Now, we've been using what's called ideal batteries. When we have ideal batteries, we basically treat them as they always have whatever value they say. So for instance, these are two AA batteries. They should have a nominal value, their spec value of not 9 volts. That would be a 9-volt battery. I didn't get that out. 3 volts, 1.5 volts for each of them. And they would add together to be 3 volts. Okay. Now, we treat them as having a resistance of 0 ohms. Basically, they just supply a potential difference, 3 volts in this case. So when we have a battery in our circuit diagrams with an ideal battery, we don't pay attention to any effect that it has on the circuit other than, in fact, let's make this a little bit simpler. I'm going to put this in with a, let's call it a 100 ohm resistor. Great. So we've got this with a 3 volt supply and 100 ohm. Now, when we go through and we apply Ohm's law on our simple circuit, we would find that our current should come up to 0.03 amp. That'd be 3 volts divided by 100 ohm, also known as 30 milliamp. In real life, however, and this is one of the things that we've seen, first off, real batteries are not always right at 3 volts. In fact, let's take a look at this. I'm going to turn on my voltmeter. Put them in parallel, and I get, this is 3.04 volts, so pretty close. That's good. Let's check one of the other ones. 3.02. Oh yeah, I put fresh batteries in these. Okay, anyway, let's see what happens when we do the following, though. Here's what I'm going to do. I'm going to connect this real quick to a light bulb. In other words, connect it to a load is the technical term. Basically what that means is, let's connect it to something and get some actual juice flowing. Now this one used to be 3.04. Let me check what the potential across it is now. 2.87. Now this is why I said, when we're doing stuff with labs, the numbers might fluctuate some in real life. And one of the big reasons for this is there's something else with these batteries. Now, we treat them as ideal batteries unless you are instructed to do so otherwise, because that's more or less what it says on the AP exam. But in real life, real batteries have something called internal resistance. And basically what it means is this. We have charges that are moving through our circuit. Technically negative, but we always treat them as positive charges moving from the high potential to the low potential, and they're moving through the circuit. They have a hard time moving through this resistor, because that's the point of a resistor. In real life, the wires have resistance as well. It's just really, really low. They're going to be a fraction of an ohm. We want them to let electricity go through very easily, so we try and keep them pretty low. It turns out that as the charges are moving through the battery, they actually have a hard time moving through the battery as well. And anytime we have charges having a difficult time moving, we call it resistance. Now, this is a special case. We call it internal resistance so that we've got a name for it. But basically what it means is, in real life, the battery acts like we've been treating it, but built into it is a small resistor. Now, that resistor has some possibly unknown value or a value that's been given. Usually for a battery, you'd want it to be relatively low, so maybe like 1 or 2 ohms or something like that. But there is going to be a little bit of resistance to the charges moving through the battery. It's kind of hard to move through a battery. A lot of times what we'll do is we'll draw a box around this to let you know that this is your real battery. It's got the ideal battery in there that is supplying 3 volts, or when we hook it to load, it turns out that it goes to 2.97. And just to make certain that you may be thinking, oh, well, that's just because it drains some of the batteries. No, because if I take it back off of that, we end up back at 3.04. When I get a good connection on there, it's bouncing around a little bit. But in real life, when you connect the battery to something and it starts drawing current, it will actually change the total amount that it has available. Because basically what we're doing is we're measuring the potential difference from here to here, delta V. Now, if this isn't connected to anything, then there's no current. And that means if we were to treat this as a separate resistor, which is more or less what we're going to do, then this would have no current, or current, I, equals 0, and that means that the potential drop across the resistor is also 0, and so all we get is the total potential of this, say 3 volts. If, however, we connect it to a circuit and it starts letting current go through, and our current is no longer equal to 0, let's say that we have a current of, well, let's go with what we said before, 30 milliamp. So let's say that we had 30 milliamp, 0.03 amp going through this. All right. Now that was based off of us having the 3 volts, but I'm just giving you an idea here. We would have 0.03 amp here because our current has to be the same as we go through that circuit, at least our total current. And all of it is going through the battery. We now have a potential drop across this because we have a current and a resistance, an effective resistance, and internal resistance. Basically, a real battery has to be treated as though it's an ideal battery with an internal resistance, a little resistor put right in with it. And we can't get rid of that because it turns out that it's actually kind of hard for charges to move through a battery. Not terribly hard, but a little hard, and that will affect the outcomes. Why is it when I hook this up, I suddenly no longer measure 3 volts anymore? Well, that's because of the internal resistance. Now, I could be going through on this a little bit better, but let's just take my current of 30 milliamp, even though technically that was found with 3 volts and a 100 ohm. Let's just say that we have a resistor here, R. Let's find out what our potential difference would be across the total battery, because now the battery is raising us up by 3, but this resistor is lowering us down a little bit. It's taking some away from it. Now, you may be looking at it strange going, well, how is it lowering it down before that? Remember what I said with these, that order doesn't really matter because all the charges have to move together. So you can draw it this way if you'd prefer. The important thing is we've got a battery and effectively a resistor in there. And now when I multiply these out, I know that my delta V, well, that would be 2 ohms times 0.03 amps. So my delta V across this resistor would be equal to 0.06 volts. Now, the battery, the ideal battery, is trying to raise us up by 3 volts, but built into it, we have something that's already bringing some of this stuff down. So our total delta V over here, if we read across it, is going to be, well, the battery is going to lift us up by 3, but that resistor is going to bring us down by 0.06 volts, and I would then end up with maybe 2.94 volts. It'll register a little bit less, which is exactly what happens in real life. I've got these happy little characters here. I connect them. We've got about 3.04, maybe 3.05. And then I connect the light bulb, and I get some charges moving through. And in real life, the charges moving through the battery, because of its internal resistance, is going to affect some of the circuit and take the overall potential and lower it some. 2.86. Now, we could go through and we could try and find the actual internal resistance of this battery, but I don't actually want to do that because I don't know what resistor I've got here. I could bring in a known resistor, a 100 ohm, for instance. We end up with the following. If I hook that up, now we're at 3 volts, almost exactly. Okay, well, let's play around with that just a little bit. My biggest problem was I didn't have a good idea of what that light bulb was. So let's take a look at this and see if we can predict what the internal resistance is for this battery pack. Technically, it's 2 batteries, but they've also got a little bit of equipment that's built into them as well. So that may be factoring into it. Okay, so we know normally that it has a total of 3 volts. Great. And then when we connect it, 3.04 volts. 3.04 volts. And that when we connect it like this, now that's with us not having it connected to a circuit and letting none of the charges flow anywhere. We've got a resistor here and then an internal resistance right here. And here's our battery. Now, when we've got this set up with the 100 ohm resistor, we've got that this ends up with a potential difference of only 3 volts. Great. Okay, so let's double check that. Now that I've got that going, in fact, I should be careful not to leave that going, because this thing's just going to get warm. 3 volts. Okay, we know I've now measured it across the resistor, and the resistor is saying that it has a potential difference of 3 volts. Great. So I can do a little bit of Ohm's law on this, and I know that the current going through the resistor is equal to the 30 milliamps that we had earlier. It turns out that worked out pretty well, because I've got pretty much exactly 3 volts. Great, and it's a 100 ohm resistor. Now I will point out, we're assuming that this is perfectly a 100 ohm resistor. In real life, it's probably like a 105, but this is good enough. All right, we therefore know that this has a current of 0.03 amp going through it, because our current is the same. We don't have any branches here, so it's our total current in each case. We also know that the battery is now registering that it's got 3 volts, but we know that overall, if no charges were going and this resistor wasn't doing anything, that it would be 3.04. So we know that the potential difference across this resistor, delta V, is equal to 0.04 volts, and that the current going through that resistor is 0.03 amp. Great. And so now I could find the internal resistance of the battery, because that's the potential difference across it, and this is the current going through it. So I end up with 0.04 divided by 0.03, and I end up with a resistance of 1.333333, although in fairness to my usual way of doing things, let's round it to 3 significant figures, 1.33 ohms. Now, is that really the internal resistance? It's going to be very close to that, but I'll remind you, that's with us having a 100 ohm resistor, not a, 105 that it likely is. In fact, let's double check that real quick. I'm going to set this to milliamp. Let's see what we get on our current. 27.6 milliamp. Why? Well, because this probably isn't exactly 100 ohms. So I could go through, I could reset this, not with 0.03, but 0.27, 27 milliamp. And now I could recalculate this. I'd have 0.04 divided by 0.027, and I would end up with a better estimate, a real-life estimate for my internal resistance of 1.48 ohm. Once again, it's a pretty small number because batteries, we try and keep them where they can have the charges move through there pretty easily, but because of the way battery technology works, there's always going to be a little bit of resistance in real life for a real battery. So here are some ways that we could go through and solve for internal resistance. For the most part, just draw your circuit, and if it's a real battery, put an additional unknown resistor or known resistor, if they give you the internal resistance, right there in series with the battery, and that's how you treat internal resistance. Okay, so real quick, I was going to have us check one other thing. It helps if you're going to try and make a measurement of the internal resistance or work with it, make any predictions on it. It helps if what you've got it connected to is a pretty low resistance value, because usually the internal resistance is going to be a pretty small number. It's not going to be like 100 ohms or 1,000 ohms. It's probably going to be around 1 ohm, maybe less, maybe a little bit more. It depends. The real life value that we estimated based on some of the stuff we had was that it's about 1.5 ohms. So here's what we're going to do. We're going to try this with something where 1.5 is a noticeable amount of it. We're going to hook it up to a 10 ohm resistor. The big problem is with the 10 ohm resistor, we could have a bit of a fluctuation. So I'm going to try and measure this. My ohm meter is telling me that it's about 12.2 ohms. Don't always trust that, but about 12 ohms. We'll call it 12 ohms. Okay, So our total resistance for this circuit with the internal resistance of the battery that we estimated to be about 1.5, though we could make some additional measurements on that. Like anything else that we've done, if I want to get a really good value for it, I should set up a lab where I take multiple measurements with different resistances. So put this and the other part together and we could probably get a pretty good value for it. Our equivalent resistance is going to be something like 13.5 ohm. 12 ohm plus the 1.5 internal resistance of the battery. If our potential across it, in fact, let's double check our potential. It's about 3.06. Okay, batteries are getting their second wind because I've been using them some. All right, so if we go through and we solve with that, our potential difference across the total the total circuit is supplied by the battery. It's 3.06 volts. Some of it will be here, some of it will be inside the battery itself in the internal resistance. That's what causes the battery to appear to drop in its supply, is the internal resistance. Okay, so then I end up with my current. We predict a current somewhere around 3.06 divided by 13.5. We end up with a predicted current of about 0.227 amp or 227 milliamp. Somewhere around 230 milliamp. Remember, to this, we're at best dealing with maybe two significant figures, so I should probably call this 230 milliamp in my prediction. All right, so here we go. Oh, I know that my scale maxes out at 200 milliamps, so I'm going to have to adjust this some. So yeah, we're going to be stuck with the two significant figures anyway. Here we go. I'm going to connect this and then measure the current. Here we go. It's going back from 0.22 to 0.23. So we're looking at about, my actual measured is 220 milliamp, possibly upwards of 230 milliamp. It's only giving me the two significant figures because that's the setting that I have on there. So it's probably somewhere around 225, which is pretty similar to what we've got there. So this is how we can work with internal resistance and what it has an effect on the circuit. Depending on what you connect to it, it will cause the values of the battery, the potential difference, a real battery, to fluctuate a little bit. And we can describe that as having an internal resistor built in because there is a little bit of resistance as charges try and move through a battery.